Yeah, we can start now. So welcome to the live session for week 7 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dikshit. Um, and I am Anant Singhal, PhD student from IIT Jodhpur, and I'll be assisting in solving similar assignment problems which have been given to you in the week 2 assignments, week 7 assignments, and that will help you to gain some better concepts and try to solve the problems with more clarity. So as we have now come to the second part of the course, which is mostly related towards the modeling aspect. So as you can see, we have already covered all the devices, all the important devices that we need to cover. We started with uh, some of the basics of the semiconductor, like what is the materials, what are the properties of the materials, and why do we call it semiconductor, and how we come up to this density of states, mobility, etc. So there was a one important function which was Fermi Dirac function, you remember. So this is most of the models are based upon this Fermi Dirac properties only, and the distributions function that you see in this particular lecture will be related to the Fermi Dirac distribution function only, and we'll be seeing that what are the effects of temperature on Fermi Dirac, etc. For this particular topic. And in this lecture we'll be covering the semi-classical transport theory, which is majorly based upon electron as a particle having some of the effective mass. So this will be the theory that will be seeing some of the topics such as distribution function. Then we have some more important Boltzmann transport equations, RTA, etc. And then at the last, there are a few topics related to scattering and mobility of the carriers. So like we have given a short of to this in this particular lecture only, in which we studied about what is mobility, but we'll see with in terms of the impurities, like what are the scattering mechanisms and how is mobility affected by that. And since we have already covered such some devices such as PN junctions, BJTs, and in the last lecture I did cover most of the MOSFET. So yeah, so we have also covered the MOSFET, some MOSFET in the previous lecture only. So with this, maybe I'll take an initial numerical for the MOSFET to redo. So we have already covered this MOS cap in the previous lecture. So now I'll take an initial numerical for the MOS cap to uh, to maybe revise the concept, because we have done the class like 2 days back only. And after that, by telling several quick facts about the MOS cap or MOS cap, yeah, we'll see some of the quick facts about MOSFET, and then we'll be covering these topics such as the distribution function, the scattering mobility, and the RT constants, etc. So let's start to the class now. This was a very basic introduction. So as I said, we have covered this MOS cap. We have three different regions here that the MOS cap operates in. We already covered. One was accumulation. Then we go towards the depletion, and at last we have a inverted channel, or the inversion region, you can say. So with this, I mean, with the understanding of this, we ended the previous lecture. Let's do a quick numerical based upon this only, and try to refresh the concepts. So let's say we have a MOS capacitor. So I want a quick solution, so please don't take much time in this. So let's say we have a MOS capacitor and we have HFO2 as a dielectric. Instead of SiO2, we have HFO2 as a dielectric, which are epsilon HFO2 of 25. The relative permittivity is 25. So for SiO2 it was 3.9, if you remember. And let's say we have a p-type substrate, and for the p-type substrate we have the electron affinity of the semiconductor given as 4 electron volts. Then we have Eg of the p-type substrate, which is 1.5 electron volt. It is also given. The relative silicon permittivity, we can take 10 instead of 11.7, which is the actual value. The Ni we can take 10 is for 12 per centimeter cube for this particular numerical. Since it is p-type, so N is also being given as 10 is per 18 per centimeter cube. And also the gate is also made up of a metal. So I mean the the work function of this particular metal is also given, which is 5 electron volts, and the oxide thickness is left. So Tox is also given as 100 angstrom for this numerical. Okay. Yeah. And there are some fixed charges also which are denoted by QSS. As you remember in the VFB calculation, they are also given as 5 10 raised per 10 Q coulomb per meter square. So this Q is the charge, the electron charge, that is 1.6 minus 19. So they are QC by centimeter square, not meter. Yeah. So we need to calculate all the three aspects that we have already covered. The first one was VFB. The second one was XD, that is the depletion width, the derivation that we did in the last lecture. And at last, we need to calculate this threshold voltage. Uh, is there any problem in understanding the question? Please do let me know because I need to give you like 5 minutes to solve this out. So if you have any problem in the question itself, please do let me know. Okay, so it seems you don't have any problem. So please do the solution one by one. So we'll start with the VFB. So quickly let me know what will be the VFB and how you will calculate it. So I can write a formula for that. I mean, we have already discussed. So formula, if you remember, so let me write solution. The formula was, if you remember, it was nothing but the difference between the metal work function and the semiconductor work function. And if there are any charges, then it was minus QSS dash by Cox. So phi m is phi m minus phi s. So this is given in the question. This is given in the question. So C ox you can find since T ox is given, and phi s you need to calculate, like you need to apply some mind to calculate this phi s. So once you are able to do it, then rest of the question is very easy. So yeah, give it a try and maybe take 2 to 3 minutes, and then I'll see what we can do. Is it fine?
Yes, sir. Yes, sir.
Any solution yet for the 5s only? Okay, any guesses how can we calculate 5s for this particular problem? So this is E vacuum. Yeah, and since we have a p type substrate, this is EF. That's EFP. So what will be the 5s in this particular diagram? So it is the difference between E vacuum and the Fermi level. So this is 5s, that is what we need to calculate. So this is EC, this is EV, and what other things we can have? We can have the electron affinity, which is the difference between vacuum and the conduction band. So this is 5s, sorry, chi s. So this is given the question. Then we have EC minus EV given the question, which is the band gap. So this is nothing but, so the band gap, the EI and the EC will have EG by 2, and this is nothing but EI minus EF, so which is the Fermi potential. So how you can calculate 5s? Then calculate 5s by summing up the electron affinity plus the Eg by 2 and plus the Fermi potential, which is 5f, or you can write this as Ei minus Ef if you want. So this is how you can calculate 5s, and then once you calculate 5s, so 5ms we can have, and once we can have 5ms, so we can keep this here and everything else is there, and Cox is nothing but epsilon ox by Tox. So this is given, so you can have Cox also. So we can calculate VFB by this. Make sense? Any doubts?
Sir, after finding 5s,
Yes.
next step will be, sir?
Next step is to calculate 5ms, and then keeping this 5ms inside VFB.
Yes, yes, sir, yes.
Yeah, so have you calculated
Then
5s?
by your formula, sir?
Yes, I mean, based upon your understanding only, I have just given you the way to calculate the 5s. So it will be calculated using like, I mean like this only. Okay, so let me calculate. So chi s is 4, Eg by 2 will be 1.5 by 2, and the third term is Fermi potential, so that will be 10 raised to power 18 by 12. Okay, so phi s will come out to be 4 plus 1.5 by 2 plus Vt ln 10 raised to power 18 by 10 raised to power 12. So this is 4 plus 0.75, so this is 4.75 plus, if you calculate this, this will be 10 raised to power 6, and ln 10 raised to power 6, so this will be 0.359. I'm not wrong, which will give your phi s to be 5.109 volts, or electron volts you can say. No, it will be volts since this is not Q times phi s. So we already have this, so phi ms we can now calculate easily, which is nothing but phi m minus phi f, and phi m is already given 5 minus 5.109, so phi ms will be nothing but minus 0.109 electron volts, or volts, whatever the unit is. Since this is not Q times phi ms, so we can write volts only. So once we have phi ms, so VFB is nothing but phi ms minus QSS dash by Cox. So Cox also we can calculate by epsilon ox by Tox. So in this particular question, we have HFO2 as a dielectric, so that will be 25 times 8.854 times per minus 14 farad per centimeter, and Tox is already given, which is 100 angstrom. So 100 angstrom in centimeter is minus 8. So we can calculate Cox from this. So minus 6, this will be minus 8. So it will come out to be 2.2125 microfarad per centimeter square. I've also given a formula in the previous class using which you can calculate directly. So Cox was 3.45 by Tox in nanometer. The unit to this is microfarad per centimeter square. So if you just keep 100 as the Tox, sorry, this will not work here because this 3.45 is for epsilon ox as 3.9. So you should not use this.
Sir, board is not visible, sir.
Sorry.
Sir, your screen is not visible.
Okay, I can see that. Okay, let me check. Is it visible now?
Yes, sir. Yes, sir. Yes, sir. Now it is visible.
Yeah, so we have also calculated Cox. We have 5 ms, we have QSS. So now just the calculation part is left. So VFB will be minus 0.109, with that is 5 ms minus QS. So that is 1.6 10 to the minus 19. And then we have this capacitance, that is 2.25 10 to the minus 6 for the microfarad. So to solve this term, so this is minus 9 minus 3 will be there. So it will come out to be, the whole solution will come out to be 0.1126 volts. This is the VFB. So we have covered the first part of the problem, that is the calculation of VFB. Now we need to find the depletion width. So we do have a direct formula. So can you tell what is the formula to calculate the depletion width? Okay, so it is nothing but 2 epsilon s pi s by qna, or phi s is 2 phi f, so that is 2 epsilon f, sorry, not 2, now it will be 4 epsilon s phi f by qna. So xd is under root 4 times, okay, semiconductor affinity, sorry, permittivity is given as 10, 2854 times 1 minus 40 times 2 phi f. So 4 I have already done, so phi f we calculated 0.359, and q is same, n is 10 to the 18. So this will be the answer. Once you solve it, this will come out to be 2.82 times 10 to the minus 6 centimeter, or this is 28.2 times 10 minus 7 centimeter, and this is nothing but a nanometer. So xd will come out to be 28.2 nanometer. So we have also covered this now. Now the third part is the VT. You see it in black. So third part is now VT. So we did a long derivation in the previous class for VT, and we got to know that VT is nothing but, if you remember, it is nothing but VFB plus Q depletion by Cox plus 2 phi f. So we have this, we have calculated this, we have Cox. So Q depletion, we do have a formula. We can even calculate directly for this QNAXD, because we have already calculated the XD. So this is 1.6 10 to the minus 19, N is 10 to the 18, then we have 2.82 times 10 to the minus 6, which is the XD that we have just calculated here. If you solve this, this will come out to be 4.512 minus 7 centimeter per centimeter square. So now we just need to keep all of this in the formula. So VFB is minus 0.1126 plus Q depletion is 4.512 times 4 minus 7 by Cox. Cox we have calculated in the previous part, that is 2.215. microfarad per centimeter square, and at the last we have 2 times of 3.359. If you calculate this will come out to be 0.204 plus this twice of this, it is 81718, and by using the final calculation it will come out to be around 0.809 volts, which is the answer for the VT. So we have calculated each and everything that was asked. So this was just to familiarize you with the previous class. So let me write the answer. So VFB came out to be minus 0.1126, XC came out to be 28.2 nanometer, and VT came out to be 0.809 volts. Is it fine?
Yeah, sir.
Okay. So one part that we didn't discuss was the CV characteristics for high frequency and low frequency. So let's quickly do that too. So for the CV characteristics, what we do, since we will have like a capacitor, so at the input we apply a certain DC and a small signal with the AC. So let's say this is the VG, that is the DC bias that we are applying, and this is some frequency small VG, let's say, and having some sine 2 pi ft with f is the frequency. So this is the experimental setup that we use to have the CV characteristics, because capacitor blocks the DC, and we know that in layman terms this is the difference in charge by voltage. And if you remember, we started with something like a constant line for a parallel plate capacitor, and we knew that this is the oxide capacitance, and for this we have epsilon ox by T ox, and we added a semiconductor in between, in which the first case was we started with the accumulation where the gate voltage was nothing but less than the flat band voltage. I hope you remember all this because I'm not going in very detail. So just to write in short, so we had a metal, we had this insulator, let's say this is the insulator, and once we apply a negative bias, so this is the VG, so we have some sinusoidal with the DC, which is VG, and this is less than VFB. So once we apply a negative bias, what we had is we had accumulation of holes. So this was P type. So this is nothing but a COX, the parallel plate capacitor. So for the accumulation mode, if I try to make the CV, so till VFB, because we are going less than VFB, so we have still the COX. Sorry. So this is the accumulation region. So now what we'll do is we'll go towards the depletion, right? So I'll update the figure in this part only, but I'll explain it. Yeah, so for the depletion, what was happening for the depletion, if you remember? We have a metal, we have again a oxide, but for depletion what we have is we have a AC plus a voltage which is let's say less than VFB, oh sorry, greater than VFB but less than VT. So by this what we were able to do is we were able to have a depletion region. So this itself has its width, right? So we have two capacitances, one is the oxide one and one is the depletion one now, because it is also like a depletion layer and it is nothing but a capacitance only. So I can make this equivalent. So first capacitance is C ox, and series of this there is one more capacitance which is C depletion. And if you know that the equivalent capacitance will be lesser than these, and it will be the parallel formula, which is C depletion into C ox, C depletion plus C ox. So this is how the capacitance starts to reduce. And since we are going less than VT, so let me update this diagram. So VT is something positive. So what happens now? Sorry, depletion, sorry, the capacitance starts to reduce. So this was accumulation, and this is what is depletion. Now the third case is, sorry, third case is nothing but inversion. So let me use red. So in this case, we completely inverted the carrier. So what we have is, we have a lot of positive at the gate, again the same thing, but the Vg this time is even greater than that of Vt. So we have an insulator, and with that we have a lot of electrons in this inversion layer. So this again acts like a positive to negative COX, and this nothing but this is like a metal layer only, because we have a lot of electrons now present at the semiconductor oxide interface. So this is equivalent to nothing but COX. And yeah, so once we go now, so it starts to increase towards COX, but yeah, it never increases beyond COX. So this is now the final CV for low frequency. So low frequency is when we are sweeping the DC voltage very slowly, like because what we want is, we want to have this inversion layer. So if we start sweeping this positive ions so quickly that these inversion layer will not be able to form, then there is no point of having this conversation. But what if we apply a very high frequency of voltage? High frequency characteristics we'll see now. So by high frequency, I mean the AC signal is very high. So what do you think will happen to the CV? So this is currently the low frequency CV. So what do you think will happen to the high frequency CV? Will there be any change? Okay, so if I talk for the accumulation part, because accumulation is nothing but the application of a negative voltage, or a voltage which is even less than flat band. So there will be no formation. We do not need any extra electron to get created, because we already have the majority carriers holes, right? Because that will not take much time to be present at the semiconductor surface. So accumulation region remains the same. Similarly, we have the minority carriers already present in the depletion region, so the depletion region also remains same. But what if now in the inversion layer, what we want is, we want to have the thermally generated electrons at the semiconductor interface, so which is just we made here. So to create this, we should not go to the frequency above the thermal generation rate of this electron, because these electrons are getting thermally generated. But now if the frequency is so high, or if the generation of electron is not fast enough to respond to this high frequency variation, what happens? This capacitance never forms. I mean, it gets stuck to the C depletion, because this region will still be depleted of the carriers, and it will act like a depletion region. So what I can say is, for the high frequency, only inversion region changes. Since the thermal generation of electron is not fast enough to respond to high frequency variations. So if I talk in here only, let me use green only. So the depletion region will remain same, and after that we will have the depletion capacitance as is. So this is the characteristic of high frequency CV that we saw in the previous lecture with some problems also. Is it fine? Does it make sense? Any doubts in this?
So, sir, it means that in low frequency, the in inversion,
Hmm.
the capacitance will be. mode,
Yeah, because
and
the
in
thermal carriers, we have the electrons at the semiconductor oxide interface, so it is like a COX. So we have the ramping up of the capacitance from C depletion parallel to COX to COX. So in the previous case, as you see, we have a combination. But in high frequency, what
yes,
happens? This always remains the same because we do not have the electrons here. We have applied so high frequency that we are not able to generate these electrons that we want to invert. So that is why this gets stuck to seed depletion and it remains the same for high frequency.
sir. Sir, actually, I just want to know that
Hmm.
in high frequency, sir, again your board will be not visible.
I can see it and it is also moving. So yeah, it is your side, I guess, the problem right now.
Okay, okay, okay. Oh, 1 minute, sir. So I can say that in high frequency, the depletion, high frequency inversion mode, in high frequency inversion mode, the carrier will be so much high concentrate that that capacity will be decreased.
No, it will not decrease, but it will never go up to COX again because we do not have these thermally generated electrons at the interface. So it will remain here only. Even if
Okay,
you
okay,
apply more VT, these electrons will not be thermally generated for the case in the inversion layer. So that is why you
okay,
see
okay,
it gets
okay.
stuck in the depletion. So this is the depletion capacity as you can see. So yeah, this was the basic of CV for both high and low frequency. So similarly, till now what we were doing is we were taking the P type substrate. So let me give you a quick overview. If we would have taken N type, so everything will get reversed. So it will start from the positive voltage. So this will be the accumulation for N type now because everything will get inverted. Then we have a depletion till VT. So this is the depletion. This is the VT. This is the VFE. So this is for N type substrate, that is a PMOS. And after VT we again have this, sorry, we again have this increase. Yeah, so this is inversion. So this is low frequency because it went up. Similarly for high frequency it will be just like this. So the red one is a high frequency plot. This is for a PMOS or CV. The one we draw or once we understood, so this was the CV for a P type substrate, that is NMOS. So yeah, this is quite a summary for the MOSFET. And then, sorry, so the MOSFET is nothing but a enhanced version of MOSFET only. So let me draw that also quickly. So what we have is we have this extra substrate. So as I said, we do not have those thermally generated carriers for the case of high frequency. So what we want the carriers beforehand. So this N plus will be a source of electrons. So this is what we name as source. This is drain. This is this is gate, and there will be a channel formation once we apply a voltage greater than that of threshold voltage, and this is the body terminal. So in circuit what we make is we draw it like this. So this is the input gate, this is drain, this is source, and the body, I mean, we in general not draw it, or if we even if we draw it, it is like a terminal like this. So what you will see in the diagrams, it will be like this only: drain, gate, and source. We do have two different types of MOSFET, but yeah, what we in general read is the enhancement type of MOSFET, which is this. The second one is the depletion MOSFET, but we are not going into that because that is not the part of the course. So in enhancement MOSFET, once the VG reaches greater than that of VT, we have conduction, and we now do have two different cases that we have discussed in the last class. The current, so I'm not doing a derivation for that because it is a very long derivation. So what we have is a final current equations, if you remember. I've already told them in the previous class. I'm not repeating those. So yeah, then that is more of it. And there's one more concept, that is the body bias. Like what if we apply a certain bias at the body? That is the only thing left to cover for the MOSFET. So let me quickly do that. That will take 5 minutes only. So what if we apply a certain body bias, or we also call this a substrate bias? So okay, so let me ask you only. So this is n plus, this is n plus. Now let's say this is body. So let's say this is B and this is the source, this is the gate, and this is the drain. So what we do is we apply a certain voltage across this VBS. So let's see, this is basically this ground right now. So let's say this is plus minus, so this will be VBS, right? So if I say VBS is greater than 0, so this is P type. So you see here B and S are like a PN junction. So there is P and there is N. So if VBS is positive, what do you think, the PN junction will be in forward or reverse bias?
Forward bias.
Yeah. Why? Because we have a positive voltage at the B and the negative voltage at the source. So it will be forward bias. Similarly, if VBS is negative, the PN junction will be reverse biased. Right? So what we have in general, what we have seen that VBS is always 0 to achieve inversion. What we have phi S as 2 phi F. This is what we were doing till now. But what if we apply a certain bias? So if you are applying a reverse bias to a PN junction, that is this case, so VBS is less than 0, or I can write this as VSB is greater than 0, right? I mean, these two are the same things. So now to get inversion, if there is some positive voltage here, we need to apply. So if we are doing the reverse biasing, we need to apply some more voltage at the body to get the inversion back. So this phi S will be nothing but 2 phi F. Since I have written VBS only, so let me write VBS for easier understanding. This minus VBS, or phi S is nothing but 2 phi F plus VSB. This extra voltage will be required at the body terminal to achieve the inversion that we were getting for this case at 2 phi F. I mean, this is quite straightforward. So once this phi F become 2 phi F, so there will be the effect on the threshold voltage. So this is what it will change. So in general, we are writing VGS. So let's write, so VFB will remain same because we do not have any change. We have this Q depletion, if you remember, by Cox plus 2 phi F or phi S. So this was the ideal case. So what will change in the after the application of body biases? This will be remain the same, that is phi ms. So the Q depletion formula, if you remember, it was something 2 phi s, sorry, 2 epsilon s q na, and we have phi s. So phi s will become now 2 phi f minus v bs. By Cox will remain the same, and this phi s will be 2 phi f minus vbs. So you can also write plus vsb also. That is all the same things. This will be the effect on the threshold voltage. I hope it makes sense. Fine.
Yes, sir.
Okay. So let's start with some of the questions for this week also now, since this is how MOSFET and MOSCAP is covered. So in this week we are dealing with the semi-classical transport theory. So semi-classical transport theory, what does it do is it treats electron as particle with effective mass. This is, I mean, we covered this very initially in the first or the second lecture, that electrons, if we have the particles and if they have a very low mass, we do treat him as waves also. That is the quantum theory. But the semi-classical transport treats them as particle with some effective mass. So option B will be the correct answer to this particular problem. Let me run that also. Yeah. So electrons in a crystal lattice are treated as particles with effective mass, allowing classical laws like Newton's to be applied. So this is the chemical classical transport problem. I mean, this was very basic. Yeah. So now what we have is how does the increase in temperature affect the Fermi-Dirac distribution? So you see the main important topic for this lecture, or the first topic, was distribution. So we know that the electron follows nothing but the Fermi-Dirac distribution. So now it says that what is the effect of temperature? If you increase the temperature, what will happen to the distribution function? So can you tell what will happen or what can happen? We have also covered a derivation. I mean, in the classes, if you have attended all the classes. Can you tell what is the distribution function first of all? No? Okay, let's cover the theory for this topic also. And this is a very short topic only. So we did discuss in first or second lecture that we have a Fermi-Dirac distribution function, which is nothing but the electrons in the solid obeys some distribution function which is governed by this Fermi-Dirac function, and these electrons are thereby also called as fermions because they follow the Fermi-Dirac distribution function. So we do call them fermions also. And this is nothing but this is all coming from this Pauli's exclusion principle, which states that no two electron can have the same quantum number at a same state. So, and we have this Fermi-Dirac distribution function. If you remember, this is nothing but 1 upon 1 plus exponential E minus EF over, sorry, KT. Do you remember this function?
Yes, sir. Yes, sir.
So what is Fe in this function? Fe is the Fermi-Dirac distribution function. And what does it say is that it shows the probability of finding an electron at energy level E. So there is E in the, you see, at energy level E, and that at temperature T. So T is in Kelvin, energy is energy. So similarly, what we discussed, that 1 minus Fe will tell you the probability of finding what? If Fe is the probability of finding electrons, then what will be 1 minus Fe?
Whole, sir.
Yeah. So it will be the probability of finding a hole at energy level E and temperature T. EF is again the Fermi energy level that we are doing in a lot of numericals now. EF is the Fermi level, T is the temperature, and K is the Boltzmann constant that we know. So what if, so first of all, let's discuss this Fermi energy level EF. So the first case, let's say T is not equals to 0. Since that is the question asked, so at E is equals to EF. So what do you think Fe will be? So it will be 1 upon 1 plus exponential E is EF, so EF minus EF over KT. So what will be this after solving? So it will be 1 upon 1 plus exponential of 0, right?
Yes, sir. Yes,
So
sir.
it will be 1 by 2. It is 0.5.
1/2.
Yeah, so it states that the Fermi energy level is that energy level at which the probability of finding an electron is 0.5. So let me write that also. We have already discussed these things, but yeah, since it has come again in terms of modeling. So Fermi energy level is that energy level at which probability of finding an electron, this was a problem I guess in the assignments also, finding an electron is 0.5. So now what if at temperature equals to 0 Kelvin? So if E is greater than EF, so there can be two cases, one is less than, one is greater than. So let's discuss this greater than first. So Fe will be nothing but 1 upon 1 plus exponential. So E is greater than EF. over kt. So t I have considered 0. So what do you think this term will be? 1 upon 1 plus this term will be,
e to the power infinite.
yeah, and let's say this case also this will be e minus ef. So now e minus ef will be negative. So this term will be,
Again e to the infinite.
so it will be minus infinite because this is
Minus,
minus.
minus,
Yeah. So if you solve e raised power infinite, this is infinite. So 1 by infinite, so fe will be 0.
0,
And in this case, this term will be 0 because 1 upon infinity is this. So it will be 1.
1.
So this is how we came to know this particular plot, that if we plot Fermi energy, sorry, if we plot Fermi energy with respect to energy level E, so this point, let's say this is EF, so it is always 1. Oh, so for the case when E is greater than EF, it was coming out to be 0, and for the cases when E is less than EF, it was always 1, right? So this is the actual function that we see, and once we increase the temperature, what happens is there will be some finite value. Let's say this is at T Kelvin, some temperature, right? So what happens to the Fermi distribution function? It broadens out once we increase the temperature or once we apply a certain temperature. Makes sense?
Yes, sir.
Yeah. So even if I increase the temperature more, what will happen is it will widen more and
Broader
more.
mode.
So let's say this is T2 now. So in this case, T2 is greater than that of T1. So let's say this is T1.
T1.
So this was the whole question. So this is the distribution that the model that we use. So now the question states that how does increase in temperature affect the Fermi Dirac? So it becomes broader, right? So option B will be the correct answer. Yeah. So let's move ahead now. So now the next question says, what is the significance of introducing concept of quasi Fermi? So when does we introduce quasi Fermi? What is quasi Fermi? Do you remember? This is, I guess, covered in the p-n junction class. Any idea? No? Okay. So if you remember, for a p-n junction for an ideal case, let me give you a very quick overview. So if you remember the p-n junction, ideal case means at equilibrium, let's say. So we have these p, we have this aligned Fermi level, right? So this is EF at the n side, this is EF at the p side. So this is the Fermi level which is constant. So what happens once we apply a bias? So we did apply both positive and uh, negative bias to it. I mean both the forward and the reverse bias case. So what if we apply a bias? What happens is we have two different Fermi levels at both the sides. So EF. So since it, let's say we are applying positive bias VA. So what happens is, so it will get more closer towards the EI, right? Because what we are applying is it will be more closer towards the EV because we have applied some positive bias, and this Fn will go more towards the EC because we have applied negative bias to the inside. This is NP, and the difference between these two was the voltage difference that we have just applied. So this is nothing but QVA. This is already discussed in the classes also. So sorry. So this was a built-in potential QVBI. This is QVA, and this is, we know that this is phi P and this is phi N that we already discussed. So what we have is, we have the V total, it was nothing but VBI plus VA. So it will be, it will be minus VA, and VBI is nothing but phi P plus phi n. Makes sense? So adding these two and subtracting these two will give me the V total, right? Which is this. So this is not VBI, this is V total. So this is a concept of quasi Fermi level. So we have two different Fermi levels at both ends. So this is EFP, this is EFN. So for the non-equilibrium cases, it is only used to have a modeling of the carrier concentration under the non-equilibrium cases. So option B will be the correct answer. So there is no simplification happening using the quasi Fermi. There is no increase in the band gap of the semiconductor. The material property remains the same, and there is no temperature dependence at all. So once we apply a bias, we do have some quasi Fermi levels at both the sided, and it is to model the concentration, because the concentration will change as we apply more and more bias, since it will become closer to the EV for a p type case, because we are applying more holes, or we are adding up more holes towards the p side. Make sense? Is there any doubt in this particular problem?
No, sir.
Okay, let's go ahead now. Okay, so determine the average mobility. Yeah, so there were few more important topics that were mobility and scattering, so let's cover those also. I guess those were the most important topics that we might have missed in the initial classes. So I mean, we did discuss this plot, if you remember, VDE. So this is VD equals to mu E plot. So what happens after the E critical field? The velocity saturates to the thermal velocity, right? If you remember. So this is, let's say, the sublinear region. I'm just randomly taking some values. So this is the linear part where VD equals to mu is followed, where mobility is constant. This is the saturation part where the saturation velocity remains equals to that of V set. Okay. Yeah, sorry. Can you see me now? Can you hear me?
Yes, sir.
Yeah. Sorry, my connection was lost. So this was the linear part, and this is in between the sublinear part. And at last we have the saturation. Again. Am I audible?
Yes, sir.
Okay, yeah. So yeah, this was a sublinear part. So what we have at low electric fields, we have the VD equals to mu E relation follows. So what happens? The drift velocity linearly is proportional to the applied electric field. So as we apply the electric field, the drift velocity increases till the point the velocity does not saturate at the V set. So at high electric field, that happens that the electron get more energy and get very highly accelerated, because of which they get rapidly collided, and this collision results in a constant velocity. If you remember, that is what we termed as a drift velocity also. And if I now plot the mobility versus the electric field plot, that will give you more insight. So mobility versus electric field. So what happens, as we said, that till the lower electric field the mobility remains constant, then we have a certain decrease and in the mobility, and then we have more a decrease. Sorry. So here mu is inversely proportional to E, here mu is inversely proportional to 1 by root E, here mobility is constant. So this is now the plot between mobility, which is centimeter square per volt second, with the electric field, which is, let's say, volt per centimeter. So just to align these two plots, I have given you idea. So what happens, the mobility initially starts with a constant value, then for higher electric field it decreases with the applied electric field. More the applied electric field, lesser will be the mobility, since we need to make the VD constant. So VD equals to mu E. So if we have more this, then we have to reduce this to have this constant in the saturation region. That is what is happening. Mobility is reducing and electric field is increasing in this particular plot. Is it fine?
Yes, sir.
Okay. So we have the concept of scattering now. Yeah. So which is similar to what is the effect of scattering on the mobility. So there can be two types of scattering. The first one is the How can it scatter? The first can be the from lattice vibrations, right? Or you can also call them as atomic vibrations because it is due to the vibration of the lattice only. So what happens with increase in temperature, the light rays vibration will increase, right? The more the temperature, more will be the vibrations, and more, if more will be the vibration, and more will be the scattering. I mean, this is the very basic analogy. Hence, the mobility will decrease. More the scattering, more will be the collision, and it will result in the decreasing of the mobility, right?
Yes, sir.
So it is relation. It is proportional to uh, 1 by T 3 by 2. So higher the temperature, lower will be the mobility. That is what I want to say. So this is the concept of lattice vibration. Now there can be one more vibration that is due to the impurities present. So scattering from charge potential, sorry, from charge particle, not potential, or you can say impurity scattering. So what happens in this particular case? Electrons also interact with the charge ions. So there could be some charge ions in the particle. So once they interact, such as a donor or acceptor ions I'm talking about. So in this case, it is important to see how these electrons or how much times the electron interact with this donor or the scattering ions. So if electron spends more time, let's say I have an electron which is in some lattice and it is spending more times with the impurity. So what do you think, the scattering will be higher or lower?
Sir, higher, sir.
Yeah, so the scattering will be higher and again the mobility will reduce, right? So if it spends more
Yes,
time with the impurities, the scattering will be higher and the mobility will reduce again. But now as the temperature increases, we know the thermal velocity also increases. And as the electron get more energy, so it passes the impurity without spending much time near the impurity. So as we are increasing the temperature, what we are reducing is we are reducing the time that it spends with the impurity. So what happens as the temperature increases, the mobility also increases due to the impurity scattering. And the mobility of the impurity scattering is plus 3 by 2. Make sense?
yes, sir. Yes,
Okay. Now here what happens is it is also dependent upon the concentration of the impurity. So if the number of impurities also mattered, then the what I can write is higher the impurity, lesser will be the mobility, right? So
yes,
in
sir.
total, what we write is the sorry, the impurity related scattering is proportional to T raised by 3 by 2 by Ni. So this is the final relation. And so we have just now divided the scattering into two parts. Sorry, the second, let me rewrite. Impurity, we have mu I as Ni over 3 by 2. Sorry, 3 by 2 over Ni. So scattering is now divided into two parts. The first one was, or let's say the first one was impurity. The second one was lattice. Here the mobility is T3 by 2 Ni. Here the mobility is 1 by 3 by 2. So what do you think? So if we say that we are talking about a very less temperature, so this is dominant at very less temperature because there will be lesser scattering at less temperatures. So what will be the case if we have more and more thermal velocity? The electrons will get more energy and it pass the time without spending much time with the impurities. So that is why it is only dominant at low temperatures. Where this is the case, it dominates at very high temperature because at higher temperature we will have more and more lattice vibrations. So what we say is mobility is 3 by 2 or less than, let's say, 100 Kelvin, and it is inversely proportional to 3 by 2. And from this we can make a plot. So once the first one will be the positive, sorry, the first one will be the positive slope 3 by 2 and the second one will be the negative slope. So if I now make log of that, because we need something linear, sorry, yeah, So let's do the log of both things. So log mu by log t. So now the first one will have a slope, positive slope of 3 by 2, right? Because we have taken log on both the sides, so it will be 3 by 2 something. The second one will have a log of minus 3 by 2. So it will have some negative slope, and yeah, I mean, this is how the final plot will be like. And if you try to relate it with the effective mobility or the effective scattering time, so it will be the parallel relation. So what happens? Let's say this 1 by tau c is the probability of collision per unit time. So it will be 1 by tau c due to lattice, the effective, plus 1 by tau c due to impurity. And similarly, the mobility also. So the 1 by effective mobility comes out to be mu L plus mu I, or whatever the n number of combinations we have. So let's say if we have first or second mobility, so the combination will be 1 by mu 1 plus 1 by mu 2. Is it fine?
Yes, sir.
Yeah, so we have this question now. So it says determine the average mobility with two scattering mechanisms having mobility. This is the first, this is the second. So give me the answer, maybe take 2 minutes only, because this is very easy now. Yeah, let me know what is the answer.
Sir, is this 450?
450, it should be lower. Okay, let me check. Mm, give me a minute. Yeah, so as I said that the first mobility mechanism is 300 and the second is 150. So mu1 is 300 centimeter square per volt second, mu2 is 450 centimeter square per volt second. So 1 by mu effective is 1 by mu1 plus 1 by mu2. So mu effective will be nothing but mu1 mu2 plus mu1 plus mu2. It will be 300 times 450 plus 300 plus 450. Oh, this is the two value, right? 300 or 450. No, it is 150. Okay. So this is 150. So this is 300 into 150 plus 300 plus 150. So it is 300 times 150 by 450.
100.
Yeah. So it will be 100 centimeter square per volt second, which is option D. Yeah. I hope the scattering is clear. So there is one more problem, I guess. Yeah. So again, we have a similar problem. Try to do this and let me know the answer in 2 minutes. Sorry. So we have the first mobility as this, the second as this. So total mobility will be what? Take 2 minutes and let me know the answer quickly. This is very easy. You do not even need to solve anything. Any answer till yet? So here the mu effective will be 0.125 times 0.25 divided by 0.125 plus 0.25. So this is 0.325 25 पंजा 3 10 it will be 0.0833.
0.023.
So which is option D. So yeah, this is scattering. I guess yeah, there is one more theoretical question from scattering. So let me know which is the correct answer. So there are three statements written and you need to tell if all of them are true or all of them are false. Something like that. Yeah. We have just gone through the basics, so it is very easy now.
Sir, 1 and 2 are correct.
And three is false.
1 means one the labor atom
Okay,
of
so let's see. So vibration of the crystalline lattice gives rise to phonon scattering. So yeah, this is correct. So we have two types of lattice scattering. Also have two types. One is phonon and one is optical.
photon.
Yeah. So when the neighboring atoms in a lattice oscillate in the same direction, yes. So there are two types now. So when lattice operates or the atoms operate in same direction, it is phonon, and when they oscillate in different direction, it is optical. So it says in same direction, this is right to phonon, And the neighbor this will to optical. Yes. So this is so all the statements are correct here.
All statement correct.
Yeah.
Okay.
So yeah, let's do this. This is also a good question. So it says the difference between the donor energy level. So donor energy level comes when we have a very high level of degeneracy. So it is, let's say, EC. So we have a thousands of donor level, but let's say this is ED, which is the donor level. And type of semiconductor we have EF, this is EI, and this is EV. So it says the difference between a donor energy and the Fermi level if 20% of the atoms at ionize acha. So this is what ED minus EF. This is what it is asking to calculate. Assume the Fermi direct without degeneracy is given, so G is always 1. I mean, this is also, if you know the number of ionized ions to the total donor ions is nothing but 1 upon 1 plus GDE, which is a degeneracy level, and it is EF minus ED over KT. So this is what we need to calculate. This is 1, and the percentage of doping is also given as 25%. So this is quite straightforward. So this will be 0.25 is nothing but 1 upon 1 plus EF minus ED. So temperature is also given. Yeah. So KT is also given. So this is nothing but 0.026. It is 300 Kelvin only. Yeah. So you can calculate EF minus ED, right? Just do it and let me know what is the answer.
Sir, 0.078.
0.07. There is no option like that. So, okay. So it is 1 by 0.25 will be,
Okay, okay. Sorry, sir. I made a mistake.
yeah. So give me the
Point
correct.
zero two eight, sir. 0.028, sir. Point zero.
Okay. So 0.028 is an option. Okay, so let's see quickly. So 1 plus exponential of this equals to 0.25. 1 by 0.25. So this is 4 minus 1 will be 3. If we take ln on both the sides, so it will be 0.026 times ln 3 is EF minus ED. So this is coming out to be 0.028, you are saying. This is option A. So option A will be the correct answer to this particular problem. I have a similar problem like this, I guess. One more. Let's do that also. Yeah, this is the problem. Wait, you've covered all the above, right? Huh. So again, we have a similar problem in which it says that the n-type semiconductor, the energy gap between the donor and the Fermi level. Oh, so the energy gap is given now. So ED minus EF is 0.036. We need to find the percentage of dopant ions. So basically, we need to calculate the dopant ions percentage. So this is the,
Sir, reverse of the previous.
yeah. So one thing is given, we need to find the second. So just do it and let me know what is the answer quickly. Okay, okay. So there is one more catch. So it is asking the percentage of dopant ions, not the ionized ion. So it is asking the percentage of dopant ion with respect to ionized. So it is asking the reverse of that, right? So it will be 1 upon 1 plus exponential. First of all, we'll calculate the dopant ions, the probability, that is Fe, and then we'll do the 1 minus Fe to find the final dopant ions. So Fe will be Ed minus Ef over Kt. So it will be 1 upon 1 plus exponential of 0.036 over 0.026.
026.
So it will come out to be 0 point something. Let's see what it is coming out to be.
0.028, sir.
Let's see. Mm, mm, Where is it? So I'm getting 0.2 exactly. You are also getting the same, right?
Yes, sir. Yes, sir.
So 1 minus 0.2 will be 0.8.
80%. 80,
Yeah.
80%.
So 80% open ion will be there. So option C is the correct answer. Make sense? Yeah. So we have also covered the scattering process. So which scattering process is proportional to delta under root T? So we have just checked one is greater than and one is minus 3 by 2. So it is asking which one was proportional to under root T. So first of all, we had two vibrations. One was the impurity and one was the lattice. So impurity, for impurity, what was the proportionality? It was Ni by 3 by 2, right? So this is minus 3 by
Minus 3
2.
by 2. Minus 3 by 2. Yes.
Yeah, yeah. So impurity cannot be the answer. So option is gone. So
Op,
now we have phonon. So we have two types of phonon, optical and acoustic. So for same
sir, optical,
directions,
sir.
so for same direction we have acoustic, right?
Acoustic phonon. Yes,
So
sir.
for same direction only the temperature will remain positive. I mean the power.
Hmm.
For opposite, sorry, this is not same. For opposite, it becomes negative, but the overall is positive only. So here the alpha is negative. So it is asking the plus 3, 1 by 2. So plus 1 by 2 will be the acoustic phonon scattering. So option D is the correct answer.
Okay, sir.
Then this we have one more problem. So it says which of the following is not an assumption made in the Boltzmann transport equation. So we have just seen that we have a lot of crystals and we have electrons getting vibrated, or this is the lattice vibration, this is the interaction. So these are all comes out from the Boltzmann transport equations only. So it is asking about the collision, which of them is not an assumption. So can you tell from the options?
Sir, is A, sir.
It is asking not. So
Oh, not.
collision,
Okay, okay, sir.
collisions is always instantaneous.
Okay, okay, okay. Sorry.
That is why they lead to ultra velocity. So let's see with option C. It says carrier-carrier interactions are neglected. Yeah. So we are only focused towards the electron and carrier interactions. So this is also as an assumption.
Yes, sir.
External forces are constant over certain length. So this is also a, because we do this F equals to QE and we relate it with the numerical, and we got to know that this mobility is nothing but Q tau C by M n star. This is the derivation we did in the second class. So these three are the assumption made. So option B will be the correct answer. There is no memory effect, so it does not remember which carrier it interacted with in the last cycle. So
Okay.
option B will be the correct answer. So since we have moved towards the modeling, let's see, because the consequent lecture will be now dependent upon a lot of mathematics. So as you see, the week 8 and 9 are mostly, so as you can see now, so week 8 and 9 will be completely devoted towards the drift and diffusion. So these are the different models that we use. I mean, there are a lot of mathematics derivation involved. So I'll cover this diffusion model derivation. There can be, so they are divided into two parts. The first is I guess they have taken the second part is the generation and recombination rate. Then we have SRH model, which is the Shockley-Reed Hall model. Then we have some boundary conditions and some Newton methods and some of the applications. So the second one is mostly related to the application, but the first one is the linearization of Poissons and the Gummel discretization, etc. So we have a lot of diffusion model. So we have a long continuity equation derivation. So in this we will be covering this continuity equation derivation. Using this we'll cover the drift diffusion part. So uh, as I have already posted that the next class will be, that is the week 8 class will be on Wednesday, the coming Wednesday, that is yes 5th of March. So yeah, this is just one more thing to add, that the week 8 class is scheduled on 5th of March, uh, and the timing will be something different, so it will be 7 to 9 p.m. because I'm not available from 6 to 7. I have some other work. So in those classes we'll be covering the different diffusion, plus some of the Boltzmann transport equation will be covered inside these only, because we have already covered the approximation, the Boltzmann approximation that we have in the second or third lecture. So as you see, with the week 3 completely dealt with this mobility, the statistics, and the scattering calculation. So these this particular lecture will help you a lot. So you can see this week 3 class, and there will be something like these only, I mean some derivations related to the scattering and mobility that we have done today. So this is I have thoroughly explained in that class, the Fermi Dirac. There is some more explanation that I have not done today, but you can check that class. Sorry, this is wrong. So the red one will be more higher. Yeah. Oh, sorry, it was correct. Yeah. So T2 is greater. Yeah. So I mean, for this particular class, what we have done is we have covered this distribution in quite detail, which is the Fermi Dirac distribution function, plus the scattering and mobility in quite detail. So RTA is, I mean, quite a theoretical topic. I mean, there is no numerical based, so it is just a straight away derivation. So you can see that in the, directly in the theoretical lectures, it has been well explained also. So yeah, I mean, this is most of it, and uh, so do attend this 5th March class, that is from 7 to 9, to have the understanding of the diffusion model. So I'll be doing the derivations first, and then we'll be seeing few problems related to the same. Is it fine? Do you have any doubts? Otherwise, we can conclude this session.
Sir,
Yes.
actually, sir, means you know that, sir, the class will be very rigorous, sir. Continuously happened, so we can miss some lectures. Okay, some not more lectures. So for next class to be understanding